we are Group H, and we have chosen the paper called Focal Loss for Dense Object Detection by Facebook AI Research. And this paper introduces a new object detection algorithm called RetinaNet, which performs much better than any other object detection algorithms. But before I explain exactly how this works, I will tell you what exactly is object detection. Object detection is the technology concerned with detecting and classifying objects in an image, and there are two ways to solve this problem, which is with two-stage detectors and with one-stage detectors. One-stage detectors tend to be faster, but they are less accurate, and the paper will discuss why this is, and then it will propose a solution to make a one-stage detector with the same accuracy as a two-stage detector. Two-stage detectors will split the object detection into two separate stages. The first one will generate a set of candidate regions which should contain all the foreground objects while leaving out as many background objects as possible. And the second stage will simply classify the foreground objects that was found in the first stage. So here I will show you an example. So here we consider the entire image at first. So we will look at everything, and then we pick out the foreground objects, which are the objects that are interesting. And then in the second stage, we will use these regions that we found and we will classify them. A one-stage detector is essentially the same as the second stage in the two-stage detector, but we now have to consider everything because we didn't filter out all the negative objects. It is faster because it is just one algorithm instead of two, but it is less accurate. So here, as you can see, it is exactly the same as the second stage, but we now have to consider absolutely everything. So you can see there is a lot of negative classes and not too many positive ones. And this is why the one-stage detectors are less accurate, because of all these negative classes will cause class imbalance since there are so many more negative samples. And this will cause biased learning and it will be less accurate. So the solution to this problem is RetinaNet, which they propose. RetinaNet is made by taking a one-stage detector and using what they call focal loss as their loss function. And a loss function is just what we call a cost function in class. This focal loss will downweigh the so-called easy background samples, and these are the samples where the classification has a very high confidence. So instead, we focus our training on the hard samples. So if you see the image here, you can see the cars are hard samples, while the grass or basically anywhere else is very easy to classify, and we shouldn't focus too much on it. You can see the graph up there. We use a parameter called gamma, which is just controlling the rate of this downweighing. So you can see the higher gamma, the faster it will drop.
Let me introduce you something about loss function. First, let's look at the cost entropy function, which is used for binary classification. Y specifies the ground truth case, which can be 1 or -1. P is the model's estimated probability for the case with label 1. For additional convenience, we define PT, which refers to estimated probability for class 1 if it belongs to 1, or estimated probability for class -1 if it belongs to -1. Then the return function is like this. This function can be seen as the blue line in this graph. We can find that as a growth of probability, the loss values decreases. For the examples which can be easily classified, they can only incur small loss values, just like a huge number of easy electives. However, if summed over a large number of easy examples, these small loss values can overwhelm real cases. To address class imbalance, previous studies introduces weighting factor alpha, ranging from 0 to 1. Alpha is set by inverse class frequency. For rotational convenience, we also define FRT. Then the retin function is like this. Because the number of foreground positives is small, so the frequency of it is low, the FRT of it is high. On the contrary, the number of background negatives is huge, so the frequency of it is high, the FRT of it is low. Multiply with cross entropy. FRT can balance importance of positive and negative ones, but it doesn't differentiate between easy and hard examples. However, what we want is to downweight easy examples and thus focus training on hard examples, including hard negatives. So this paper introduces modulating factor 1 minus pt to the power gamma to the cross entropy. Gamma is a tunable focusing parameter which is known as 0. Then the focal loss function is like this. When an example is misclassified, if it's an easy example, the estimated probability for it is close to 1, so 1 minus pt will be close to 0. Then, that's the modulating factor times the cross entropy. The value will decrease, so we downweight the easy examples. However, if it's a hard example, the estimated probability for it is small, so 1 minus pt will be close to 1. Then that's the modulating factor times the cross entropy again. The values will be almost unaffected. This is the way the paper used to downweight easy examples and focus training on high examples. Gamma is a tunable focusing parameter that can determine the rate at which we downweight the easy examples. Because as the growth of gamma, the modulating factor will decrease, so the focal loss will decrease either. We can see this from this graph. As the growth of gamma, we can see that this line will be closer to the axis, which means with the same value of probability, they can only incur small value of losses. In practice, they use alpha-balanced variant of focal loss as it yields slightly improved accuracy over the non-alpha-balanced form in experiments.
So how effective is the focal loss? The researchers designed and trained a simple model called RetinaNet. The network design of RetinaNet is very similar to those dense detectors. They emphasize on the new loss function focal loss instead of any innovation in network. RetinaNet is a single fully convolutional network. It uses a feature pyramid network as backbone on top of RetinaNet. Each level of the pyramid contains two subnet networks. The upper one will do object classification for anchor boxes, and the lower one will regress from anchor boxes to ground truth object boxes. The paper said that the design is simple, but for us it's difficult. We know the design, but we don't exactly know why. Why is it simple? This is a comparison graph made by researchers. The x-axis is inference speed. The y-axis is average precision, AP. All models were tested with the same COCO dataset. As you can see from the graph, these two lines are RetinaNet with different depths and pixel scales. Those boxes are other models. Except for D and G are two-stage detectors, others are all one-stage detectors. We can see that RetinaNet can surpassing all these state-of-the-art detectors' accuracy with similar speed. RetinaNet is efficient and accurate.
So after the literature review, here's the implementation part. We deploy the project on the Google Cloud instance, and we do prediction based on a pre-trained RetinaNet model. The inputs will be raw images and the outputs will be images with anchor boxes. The project uses Keras to do both training and prediction, and the reference is shown here. Here I will show you the workflow of prediction. First, we load the necessary modules. Second, we load the RetinaNet model. I draw 3 raw images here, and using this prediction function, we can get the 3 output images with anchor boxes. We can see that the boxes whose score larger than 0.5 will be true. And here is the end of our presentation. Thank you for your listening.